Hello everyone, in this video I am going to show a colorful visualization of the motion of an object subjected to two simultaneous harmonic disturbances. So in an undergraduate syllabus there are two kinds of situations where individual vibrations act in the same direction or in the perpendicular direction, and then how the combined motion occurs depending on the frequency, phase and amplitude. So in this video I am going to show the case of same direction. So in general, the combined motion can be complicated, but if we take special cases, then some interesting patterns can be observed. Also, these special cases are relevant in many topics of science and engineering. The first case is when the frequencies are equal, and within that, what happens if the amplitudes and phases are different, or what happens if amplitudes are equal and phases are unequal. Second special case is when the frequencies are not equal. When the frequencies are not equal, we can look at a case where the time periods are related by a simple relationship, and second case where the frequencies differ by a small amount, which is referred to as beats. When the individual frequencies are same, then the resulting vibration is also simple harmonic in nature, which will have a amplitude and phase which looks like this. I'm not going into details. For details I suggest you to refer any of the undergraduate textbook, first or second semester generally. And when the amplitudes are also equal, then this is how the resultant amplitude and the phase looks. When the frequencies are different, initial phases are not so important. Here what happens is the total phase difference is a function of time, and the pattern changes depending on that. So in general the motion will be very complicated, and the displacement, the combined displacement will occur between 0 and a1 plus a2 depending on the time. So the combined motion periodic if there is a simple relationship between the time periods, which looks like this: n1 t1 is equal to n2 t2, and in such a case the phase also plays some role. So the combined displacement can be written like this. So the interesting case where omega 1 is almost equal to omega 2, or the difference is very small, is referred to as beats. The motion occurs at a frequency which is average of omega 1 and omega 2. It varies with time, which has very small frequency compared to the omega 1 plus omega 2 by 2. So the amplitude varies with omega 1 minus omega 2 by 2. And the analysis of beats also becomes very easy if the amplitudes are kept constant. Now let us look at this visualization window. We have this inputs here, oscillator 1 and oscillator 2. It can have amplitude, frequency and initial phase. Presently some initial values are given. At first let us observe how those individual motions would look like. This is oscillator 1, that is, this is the oscillator with these parameters, and this is the oscillator with these parameters, which I will be calling oscillator 1 and oscillator 2. You can see that oscillator 2 is moving faster, it has more frequency, but both the oscillators move between these fixed limits. Each one has its own fixed limit, 2.17, 1.25 for the first oscillator. So each time when it comes to the left extreme, it would visit the dashed line, and each time it visits the right extreme, it would visit the right extreme. So is the case with oscillator 1. This is one of the characteristics of simple harmonic motion. Now our interest is to see if both these two motions are present simultaneously, how would it look. So this is the equation, and this is the oscillator. For the sake of clarity, these two will be running simultaneously. Let us see. So it has gone to -1, the combined oscillator. On the right it is not going to -1, it is going 2 plus something. The next time when it is coming, oh, it has gone -3 point something. Now you can see it, interestingly it is not going anywhere, it is going to 1 and is going to -2 point something, and each time it is visiting right side, it is going to some extreme which is not fixed or So to make a sense out of this motion, whether it is periodic or not, let us plot this graph. So we'll be plotting the graph here. I will use the time slider and make a graph once this is stopped. So this is the time axis and this is the displacement from the mean position of the combined oscillator. So presently it is at 1, around 1. So next time instant it is going almost to the equilibrium. This is the equilibrium position or the some sort of a central position. Going towards the left, and it is taking a turn at -1. Let us hold. Again at this 0, going to -3 point something, crossing this 0 position, again you can see first it was -3 point something, again it is -2 point something. Let me take it faster. So it is, first it was 2, then it was 1, now it is 3 point something. So there appears to be no particular pattern. Now let us consider a case of equal frequency first and see what happens. This time I will not use the slider, but I will use this button which will move and plot the thing for us. So now frequencies are same, but amplitudes and initial phases are something different. Let us observe. First it has gone to left extreme, it has gone to right extreme, again it is going to left extreme. So this appears to be periodic because both the frequencies are same, hence the frequency of the combined motion will also be same. The only difference would be the amplitude and the initial phase. So we can see it is going between two fixed limits. At 10 this simulation would stop. Now what we will do is something interesting. Now let us change the amplitude. Now we will not see the motion of the object, we will see only the graph. How does the graph look? So as the amplitude increases, what happens? Observe here. So this is the graph for the first oscillator, graph for the second oscillator, and graph for the combined motion. Amplitude is changing, now it is about 3. We can see the frequency is same, but only the effect is on the amplitude. Now let us change the phase. Now with changing phase also the amplitude changes, but frequency is same, and initial phase also is changing. So this is the case of equal frequency, when the frequency is equal frequency where phase is changing. Now let us observe another important case where the amplitudes are also same. Let's put 2 and 2 for this, calculate. Now the frequencies are same, amplitudes are same, and let us see what happens as a function of changing phase. This is a very important case where it comes across in case of optics, though there is no motion, but it is in the context of waves. So we can see it is almost diminished. We get a 0. So let's take a little bit of it at same frequency. Now let us observe the motion for this. So you can see the amplitude is very small. It is going between two limits, around 0.6 to minus 0.6. So when frequencies are same and amplitudes are also same, the amplitude of the combined motion can be 0 to maximum, that is 4. Let's make both of them same. So this is a trivial case where both amplitude, frequency and initial phase are same, so all the three motions will appear to be happening in tandem. When it goes left, both of them are on left. When both of them are on right, the combined motion is also on the right.